Welcome to Module 2 of the Biodiesel Learning Toolkit. This module is made possible by the Biofuels for Schools program. Biofuels for Schools began in 2010 through a Together Green Fellowship in support of the Kentucky Division of Compliance Assistance. Together Green is a conservation alliance between Toyota and Audubon. The Alliance supports community-focused projects to engage local residents in conserving land, water, and energy. The Division of Compliance Assistance is a part of the Kentucky Department for Environmental Protection. DCA exists to provide services that increase environmental knowledge and encourage positive behavioral changes. DCA does this to improve regulatory compliance, achieve exceptional performance, and enhance the quality of Kentucky's environment and communities. Module 2 focuses on three main learning objectives. At the end of the module, you should understand the properties of fatty acids, be able to explain what a triglyceride is, and 3, understand the reaction Transesterification. Upon completion of the module, you will receive a certificate of completion. In Learning Objective 1, we will discuss what a fatty acid is, the components of its structure, and how that structure affects its chemical and physical properties such as melting point and solubility. Fatty acids are a portion of a larger group called lipids. Fatty acids are organic compounds, which means they are composed of carbon, hydrogen, and oxygen. A fatty acid is composed of a long hydrocarbon chain or tail attached to a carboxyl group at the other end of that long hydrocarbon tail. Fatty acids are insoluble in water and soluble in organic solvents. Dietary fats supply energy, carry fat-soluble vitamins such as vitamins A, D, E, and K, and are a source of antioxidants and bioactive compounds. Fats are also incorporated as structural components of the brain and cell membranes. This is butyric acid. Here you see two ways of representing the chemical structure of this particular fatty acid. The hydrocarbon chain is referred to as the tail. The carboxyl group is represented by 1 carbon, 2 oxygen molecules, and 1 hydrogen molecule. The type of fatty acid and its structure affects its physical properties such as physical state, melting point, and solubility. We will be discussing types of fatty acids that are saturated versus unsaturated, short versus long hydrocarbon chains, and straight versus crooked structures. In the hydrocarbon tail of the fatty acid, it is important to understand the structure as it relates to the double bonds. Saturated means that the hydrocarbon chain does not contain any double bonds. The difference between trans and cis is the shape of the molecule. Trans is more straight, while cis has a zigzag shape. This is due to the placement of the double bond. The double bond reduces the amount of hydrogen atoms on the molecule. Therefore, the molecular weight of the unsaturated chain is less than that of the saturated chain for the same number of carbon atoms. As a rule, the melting point of a molecule increases with the molecular weight. This means at room temperature, saturated fatty acids tend to be solid, while unsaturated fatty acids are liquids. This is also due to the fact that saturated fatty acids are straight and tend to stack together and bond, while the zigzag or crooked nature of the unsaturated fatty acids makes this stacking and bonding more difficult. In general, saturated fatty acids have a higher melting point than unsaturated fatty acids. Solubility is the ability of a molecule to be attracted to water. Fatty acids have two parts of their structure. The hydrocarbon side does not like water, but the carboxyl group does like water. Therefore, the shorter the hydrocarbon chain, the more the fatty acid likes water. When the hydrocarbon chain is very long, it can cancel out the effects of the water-liking carboxyl group, and thereby making the whole molecule insoluble. Long-chain fatty acids are less soluble than short chains. Here are some examples of the types of fatty acids and how many carbon atoms are in the structure, along with how many double bonds. You will also notice the sources of these common fatty acids. In Learning Objective 2, we will discuss the properties and structures of triglycerides. Fats and oils are commonly called triglycerides. Triglycerides are yet another segment of the larger lipid group, similar to fatty acids. The triglyceride molecule looks like the letter E, and this is a good way to remember its structure. It is composed of fatty acid segments, which we learned about in Learning Objective 1, and a glycerol component. Structurally, a triglyceride is an ester derived from a fatty acid and glycerol. An ester is similar to the carboxyl group of the fatty acid, except that the hydrogen attached to the oxygen is replaced by a hydrocarbon group. On the right, you will see that the triglyceride molecule contains 3 functional ester groups. When triglycerides are exposed to water, hydrolysis can occur, which converts the triglyceride back to a fatty acid and glycerol. When oil is used in cooking, the same type of reaction can occur, causing the release of the fatty acids. These are then known as free fatty acids, or FFAs. While hydrolysis is the process by which triglycerides are broken down, esterification is the process by which triglycerides are formed. Hydrolysis and esterification are 2 reactions, and they are the reverse of each other. Over time, cooking with oil and reusing that oil causes the fingers of the triglyceride molecule to break off. These fingers are the free fatty acids. When the oil is transformed into biodiesel, these free roaming fatty acids can adversely impact the reaction. In Learning Objective 3, we will discuss the chemical reaction that produces biodiesel. When a triglyceride is reacted with a short-chain alcohol, biodiesel is produced along with glycerol or glycerin. This is called transesterification. The chemical name of biodiesel is a fatty acid methyl ester. This reaction is usually done with a base catalyst. A base means that the pH is greater than 7 and is considered caustic, so safety precautions should be taken as necessary. A catalyst is something that enhances the reaction, and in this instance, the sodium hydroxide catalyst causes the reaction to move faster. Potassium hydroxide is also used as a base catalyst for biodiesel reactions. Second-generation biodiesel reactions are experimenting with enzymes as the catalyst. In essence, the catalyst acts like a pair of scissors and cuts off the fatty acids of the triglyceride molecule, allowing the OH of the methanol to form glycerol, and the CH3 or methyl group to form the three esters of the free fatty acids. You will notice that it takes 3 molecules of the alcohol to react with 1 triglyceride molecule. The equation is balanced because 3 biodiesel molecules are produced and 1 glycerin molecule. This is extremely important when using waste vegetable oil for biodiesel production. The presence of free fatty acids is like having additional materials present during the reaction, almost like when uninvited guests are over for dinner. If you don't plan for these uninvited guests, then you may not have enough food. In order to have a successful biodiesel reaction, you must know the percentage of free fatty acids in your fat or oil prior to processing it in order to calculate how much catalyst is required. Here you see a simplified flow diagram of producing biodiesel. For biodiesel to be used in vehicles, it must be refined and tested to ensure no impurities are present that could affect performance. Biodiesel must be refined in order to meet ASTM quality standards and must be stored in a way as to minimize contamination by water. As you remember, glycerin is produced from biodiesel reactions. This glycerin can have impurities such as unreacted methanol and catalyst. Refining the glycerin to remove these chemicals can make it into a viable secondary product. Glycerin can be used in soap making and in cosmetics as well as a composting amendment. The refined biodiesel should be pH neutral and clear in color. In this picture, students conducted a small reaction in a jar to produce biodiesel and glycerin. This biodiesel was made from using pure vegetable oil. Can you see the 2 layers? The biodiesel layer is on top and the glycerin layer is on the bottom.